Okay, Bismillahirrahmanirrahim. Assalamualaikum and a very good day to you all. In this slide, we are talking about shaft stress. So, this topic I taken from chapter 7, Shaft and Shaft Component Design from the Shigley book, Mechanical Engineering Design. So again, student, you should have this book beside you when you are listening to this slide. Okay. Okay, student, when you are analyzing the stress, the bending, torsion, and as a stress happen all at the same time. Okay, imagine this is a car, this is a toy car, this is a tire. Okay, when the tire rotates, see, the tire rotates, it is an torsion. It gives the torsion to the shaft. Also, it also have the bending moment. Okay, it's like fluctuating moment like this. Also, they have the axial stress like this. The one that giving the stress here and the one that giving the stress here. This is the axial stress. Okay, so all happen at the same time, and for the purpose of the calculation, there are alternating stress, meaning that the stress come here, here, here. It is an alternating stress. Also coming here, here, here. Also, it's called an alternating stress. And also, when it comes to bending, the stress is like this. Okay, also an alternating stress. You will see the next video what is an alternating stress. Also, the stress happen at the mid range. This is the mid range, right? This is the shaft, this is the mid range of the shaft. Okay. Okay, what is a fluctuating stress? You see here in the sinus graph. Okay, here the graph going up, down like this, going up, going down, going up, going down. Here present a sinus graph. Okay, and the equation related to it is stress A represent for alternating, and M represent as mid-range. So Kf is the stress concentration factor. You will learn in the next slide. Okay, so this is the stress mc per I. I is the moment of inertia of the shaft. Okay, m is the moment. C is, if you remember the class that you have learned in solid mechanics last semester. Okay, you will see what is C. Okay, this is an outer diameter of the shaft. Okay, C is the outer diameter of the shaft, where 0 uh, is the middle at the thing, and X is any point in the location of the shaft. So for this calculation, we represent C as the outer diameter of the shaft. Okay, and also there is the torque. Okay, torque is represented by KFS is stress concentration factor, T is the torque, R is the radial, and J is the polar moment of inertia uh, of the stress of the shaft. Okay. Okay. Geometric terms for C, I, R, and J. What is C, I, R, and J? Okay. C is the outer radius. Let's say this is a shaft. Okay. And C and the middle point is 0 point. C is the outer radius of the shaft. Okay, the outer radius of the diameter for the shaft. I is the moment of inertia for the shaft. R is the any point from the midpoint 0 location up until the outer radius of the shaft. This is R. And J is the polar moment of inertia for the shaft. And what is a polar moment of inertia? Let's say this shaft, suddenly it moves in 180 degrees. It is moving in a polar direction. Okay, in the polar direction. Okay, so this is called the polar moment of inertia. uh, okay, this is represented by, again, A here represent is the alternating stress. M here is the mid-range stress. You can see the equation 32 MA pi d, the power of 3. Okay, so this is the equation for the stress, and this is the equation for the torque, alternating torque and the mid-range torque. Okay, alternating torque, again, alternating is the sinus radius. Remember in the previous slide, the stress come from here, 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 and the mid-range is at the middle of the shaft. Okay. Okay, students, I will read this statement first, then I will explain. The fluctuating Budynas stress. Using the distortion energy failure, the Budynas stress is given by equation 515, page 237, with stress in axial location is stress, bending stress is 0, and the torsion xy equals to torsion, the torsional shear stress. Thus, for rotating round solid shaft neglecting the axial loads, the fluctuating Budynas stress is given by this equation. Okay, this equation. So what does this statement means? What does this statement means? Okay, it means that in order to build up this equation, okay, it is assumed that the shaft is rotate, only a torsional stress is given. This is a torsional stress, no axial stress, no bending stress, only torsional stress. And do you familiarize with this equation? It is a theorem Pythagoras. Remember here, this is 3, 4, and 5. This is a theorem Pythagoras. Okay, now we are talking about stress concentration factors. The one that you see in the previous equation, the one that the word K. Okay, stress concentration factor is sometimes considered optional for mid-range components with ductile materials because of the capacity of ductile material to yield locally at discontinuity. Okay, this is the statement. What does this statement means? Okay, let's say this is a ductile material. Okay, ductile material. What does it mean by this discontinuity? Let's say my hand here is the discontinue. This is the shaft. This is the clamp for the shaft. Okay, and then when I squeeze the shaft, became this, like this. This is the yielding. This is the yielding. I am squeezing the shaft, and the shaft become yield. Okay, this is called the yielding. Okay, and it happen only to ductile material. Ductile, opposite of ductile is brittle. No shaft is made from brittle material because brittle will fail. Okay, and this is the stress concentration factors uh, at the sharp edges. Okay, at the sharp edges it is high. The value is high at the sharp. This is the sharp edges. The value is high. This is the fillet edges. The value is low. Okay. Okay, student. This is a Goodman diagram. Okay, the diagram is represented by this graph. Remember the last slide, the previous slide, I talked about the theorem Pythagoras. The equation represent the theorem Pythagoras. Okay. Uh, if you do the equation, you put the value in the equation, you will get this value. You will get this theorem Pythagoras graph. Okay. So this graph represent the alternating stress. This is the fatigue stress. This is the ultimate stress. And according to the Goodman diagram, whatever result that it's beyond this line, it is fail. Okay. And this is the definition of the Goodman diagram according to the sources from internet. Okay, this is the fatigue failure criteria for the modified Goodman line. Okay, 1 per n is number of cycles, and then the alternating stress, then the mid-range stress, then this is the surface endurance strength, and then the ultimate tensile stress. Okay, then substitution of alternating stress and mid-range stress from the equation 75 and 76 result in this equation. The purpose of the Goodman failure criteria is to get the diameter of the shaft, and when you solve the calculation, when you solve the equation for the diameter, you get the diameter. Okay, it means that the diameter of the shaft, it depends on the stress concentration factor, depends on the moment, okay, and also depend on the torque of the design. Okay, so now we are talking about distortion theory. What is a distortion theory? Distortion theory is a failure theory that used to predict the failure of a tough material. Okay, this is an assumption that the proportion of strength causes a component to change shape is a crucial factor in relation to the material strength. Okay, you see this picture I taken from Google. Okay, it's presented by the distortion theory. Okay, this is the box. Okay, this is the box. Okay, when I put my force here, the box will distort like this. This is distortion. Okay, this is the called distortion. So the statement that says that based on the proportion of energy that cause the component to change, is that when I put the force gradually, slow and steady, it distort. Okay, this is what it means by that. Okay. Okay, this is another distortion energy by Goodman. It's called distortion energy Goodman, DE Goodman. You can see the equation 7.7 and 7.8. This is another distortion energy theory by Gerber. Okay, this is also another distortion energy theory by ASME elliptic. And finally, the distortion energy theory by Soderbergh. So all those theories, all those distortion energy theories, elliptic, Soderbergh, Gerber, SME elliptic, Goodman, and also Morrow, are all representing the failure theory. And but the Morrow, this picture I taken from Google Images. Morrow we don't discuss in the textbook. The textbook does not discuss about Morrow. Okay, so in the last slide I mentioned whatever result happen beyond this line represent failure. This is the line. Okay, this line, whatever result that happen beyond this line is a failure. Okay. Okay, for rotating shaft, the statement here says that for rotating shaft with constant bending and torsion, the bending stress is completely reversed and torsion is steady. Okay, here is a rotating shaft represented by the cardboard that I am holding now. Okay, when it rotates, okay, where are the bending stress? There is no bending stress. Bending stress it happen, but it it is more towards the torsion than bending stress. So this is what the statement say, that the bending stress is completely reversed. And then to simplify the equation, set the moment and the torque to become 0, and then the equation should be uh, quite easy. So you can see we will do the example in the next video. Okay, what is a static failure? Static failure meaning that the shaft is static. No rotation happen, no bending happen, no axial stress happen. Meaning that the shaft fail because the load is given so high, then the shaft fail like this. This is called yielding. Okay, this is called the yielding. Okay, so Soderbergh criteria give the guards against welding. What is the guard? Okay, it is because the Soderbergh criteria and also SME ability. In the end, it give the diameter of the shaft. You put in all the parameters in the equation, it give the diameter. Okay, and that diameter will represent whether the shaft can be yielding or not yielding. While the previous equation Soderbergh and elliptic guards against yielding, meaning that give the proper diameter for the shaft. This Goodman and Gerber does not guard against yielding. It therefore requires separate check for yielding. Okay, this is given by this equation and this equation. Okay, so for quick estimate conservative check, estimate for the stress can obtain by simply adding alternating stress and alternating mid-range stress always be greater than equal to stress maximum, and they will therefore be conservative. Okay, so that's all the video for now. See you in the next video. We will do some calculations.